Hello guys, back with another video and a discrete video today, but a very important one. And as you can see already with the picture in front of me, we are going to design a overcurrent circuit and a DC one. As we know, AC overcurrent is basically, you have MCBs in your house, that is basically overcurrent, and of course overcurrent handles short circuit too, and those MCBs are rated for a certain amount of current, say 10 amp, or if it's for higher power maybe 30 amps or something like that. But that is for AC, and AC has a zero crossing, and those operate on a different architecture. But our standard circuits, what all we do, are all DC generally, except for if you're dealing with SCRs or something like that. But DC is the standard, and of course sometimes people touch the contacts of the power supply together, the positive and negative, and that's a short basically. Or say something which is only rated for 1 amp and you try and push 2 amps into it, it's going to get destroyed. So we need something to protect the circuit, right? And it has to do it fast, because all these devices, the especially MOSFETs and solid state switches, they can't even tolerate overcurrent for a few microseconds, so it has to be within that. So generally, if it's a microcontroller based solution, they use hall effect sensors, then they sense the current, they sample it, and then maybe they stop the PWM. That is generally what they do. But today we're going to be implementing it in the discrete way, in the analog way. So yeah, let's go into the circuit. Yeah, I have the schematic here now on in multisim, and it looks a bit big, but I'll explain the parts, and later once you understand it together, it shouldn't be a problem. So let's zoom into this part here. This is the beginning of the circuit. This basically, you can see here, this is the IRF 4905. That's a P channel MOSFET, a power MOSFET. And why we need a P channel here is because we need a high side switch, so we can't use a N channel here. For the N channel, I'll probably have to think of some other circuit, but currently P channel is the easiest to handle and build a circuit around. So let's keep it at that. And why we need that is we need to sense current basically. Of course, if we want to sense over current, we need to use some kind of device. And what we use here is a current shunt, as they call it, which is basically just a very low value resistor but rated for a couple of watts, so it can dissipate good amount of power. And what it does is, you can't measure current as such, right, in this circuit, but you can measure voltage. So what you do is, you put your load, and in this case my load is a 22 ohm. So you put your load in series with this current shunt resistor, and the current is going to be same, right? I mean, 22 ohms is your load, and if your VCC is 12 volts, so your current is going to be 12 by 22, which is roughly 500, somewhere around 500 milliamp. And if you just add 1 ohm, it's not going to change the current much, and that's exactly what we want. We don't want our readings to get messed up because of our resistor, so it shouldn't be too high of a value, so they keep it below 1 ohm. So I have exactly used 1 ohm. So basically, if you just put Ohm's law, then V is equal to IR, right? So if we want the current, I is equal to V by I. And if the resistor is 1 ohm, then you basically have V by 1, which is just V. So basically, if you monitor the voltage across this, that is essentially going to be the current itself. So it's quite easy and intuitive. That's why I just used 1 ohm. If you use 0.1 ohm, it's going to be 1/10 of it flowing, the current. So 1 ohm is simple, and I had a 1 ohm lying around, so we'll just use that. So first of all, this is our main switch, which is, as I said, the P channel MOSFET. This is our load, and that's the current shunt. And we use the high side switch here because here, since we put the shunt between the load and ground, we can easily measure across ground and this point, this node, which is V shunt node. So yeah, we use that. And what we need, the second thing is a comparator, because we need to compare the current voltage drop, or say the current which is flowing through the shunt, with a set value, and that is going to be your safe value of current. So this is the LM311, which is a comparator. Just show you the data sheet here. It's a differential comparator. So you could use a op amp, but this is specifically designed for being a comparator, and it's much faster, and we need that. This has just 165 nanosecond delay, so that's very fast. And what it does is basically you have same as the op amp, the symbol, everything is same. You have a inverting input and a non-inverting input, and if the inverting input is higher than your non-inverting input, the output is basically, in a op amp it would go high, but if you see here, this there's a BJT here, so basically it has a open collector output, and it looks like this. So basically if your inverting input is higher than your non-inverting input, then this BJT is gonna turn on and basically pull the output to ground, just like how a normal BJT behaves. And if your the inverting terminal is greater than the non-inverting terminal, then this stays in the off state, and the output gets pulled up. And it's basically an open collector output as well as an open emitter. So you have a choice. You can put a pull down or you can put a pull up, but the pull up is standard, so I'll be going with the pull up itself. So this config, as they have shown it over here, this one. So as I said again, if this is high and this is low, then this gets turned down, output goes 0. If this is high and this is low, then this stays in the off state and your output is pulled up, so to VCC. So we have the comparator here, as I said, and what we do is we feed the drop across that shunt, as I showed you, which was V shunt, to the non-inverting terminal, and to the inverting terminal we set our control voltage, which is going to define how much our safe limit of current is, and we can do that using a voltage divider. And what I've done is, since my VCC is 12 volt, I've just used 150k and 15k. So the voltage across this is basically going to be around 1.1 volt, and since we're using 1 ohm current sense resistor, the current shunt, that basically means that our safe limit is 1.1 amps. So anything below 1.1 amp, it's going to let it flow, and above, just in case if it goes above that, it's going to turn this on and cut off the circuit. So the comparator does that, basically it just continuously compares the voltage, and the comparator's output goes to this configuration here. And if you can see this, you'd probably guess what this is. This is a SR latch made from NAND gates. So this over here, the SR latch, and normally they show the SR latch with a NOR gate, but the NAND is, both are universal gates, but this is more common. I had this lying around, the 74HC00. So this one, it's the CMOS one, since HC is a high speed series, but it does need 5 volts, so take care of that, between 2 and 6. So it has 4 NAND gates inside it, inside the PDIP 14 package, and we need all 4 of them, so that's good too. So here I'm going to be using the latch, not a flip-flop, so there's no clock, it's not clocked. So we're just going to short these two inputs and call it set, short these two and call it R. And this one will basically receive S bar, which is the complement, since if you short the inputs we are going to get S bar, and if you short these two you're going to get R bar. So, and that is going to give us the output, and the output complemented, and we'll only be dealing with the output. So we have the SR latch here, and this is basically our reset input, and this is basically our set input. So you can see that my reset input, both of them, of course, this is CMOS, so it needs a valid state. So you cannot leave these inputs floating. So I have put pull downs on both of them, since we know that if, according to the truth table of SR latch, if both the inputs are 0 0, whatever your previous state was, it would remain maintained, or no change as they call it. So we need that state, that well defined state. So I've put pull downs on both, and additionally we have, to the reset input, one path goes to the pull down, which is fine, and another input comes from the comparator's output. So in our standard condition, when the current is in the safe limit, this BJT over here would be on, so your output would be 0. So this would basically be 0 into 0 into 0, which basically nothing is going to change, and that comes from the comparator. Whereas for the set input, and another thing, of course, I forgot to mention, just in case the current goes above its safe limit, this output would be pulled up, this BJT would turn off, and this output would be pulled up to 12 volt. And what that basically would do is, get a, you get a reset spike here, which would, as we know, once the reset input is 1 of ISR latch, the output becomes 0, and that's exactly what we want. So that is for the reset part of it. And for the set part of it, what we do is, over here, one same as before, we have a pull down, and we do need a reset switch, right? That's because, let's say you tripped, something happened and the circuit tripped, which is good, but now you have fixed whatever was wrong and you want to restart the circuit again, right? So you need some kind of switch. So that's the switch here, which would restart the circuit. And you can see here there's one series RC, and that's because in the start, this is a sequential circuit because the feedback is there between input and output, as in a latch always has. So in the, we always say that qn plus 1, if both inputs are 0 0, the output would remain no change, right? But for that we need to have a previous state. So what we do is, in the start itself, we once the circuit is going to be powered on, we just put a series RC to the set input. So initially this capacitor would act as a short. So basically we would get a 1 at this set input. And if you set the input 1 and this would remain 0, your output becomes 1. So our initial state would be 1, and that's exactly what we want. So now that this is there, the output of this SR latch is fed to basically two parts. One part is our NPN BJT, and that's just a driver, and that leads us back to our original P channel MOSFET. And since the P channel MOSFET, it needs to be, in order to turn it off, we need to bring the VGS close to 0. So for that we need this driver. We can't directly drive it from the SR latch. So yeah, in case this SR latch is off, the output would be pulled up, and this basically, this is 12 volt, this is 12 volt, the P channel MOSFET would be off. And in normal conditions this would be on, so our output would be 0, and that would create a VGS of around minus 12 volts, and the basically that would keep the P channel MOSFET on and your current would be flowing. And to just show that the current is below the limit and the circuit is operating properly, we have a green color LED here. You can see the color right now. I'll show it to you on the breadboard, but the green colored LED would signify that it's the safe operation is going on and your circuit is behaving normally. So we have that here. And also the SR latch is driving another BJT here, and you could see this was a NPN BJT, the BC547. This is the BC557, which is a PNP BJT, and we need a complementary pair, so that once this is on, this will not be on, and once this is on, this will not be on. And that's can be easily done with PNP and NPN BJT. You don't need a MOSFET here. So the output, same output, drives a PNP BJT, which as I said would work complementarily. So let's say there's a fault, right? So your P channel MOSFET has stopped and the current, some overcurrent event happened. Now the circuit is turned off. You need to know that, right? That, oh, the circuit has tripped. So we have, this would basically, the output of this would be 0, and if that is 0, then that would basically turn this PNP BJT on. And once that PNP BJT turns on, this is going to be a red color LED, which should signify that overcurrent has happened and you need to reset the circuit. And sometimes even visual, or along with visual, audio also helps. So I've put a buzzer also, a 5 volt buzzer. So yeah, if in normal cases this NPN BJT would be on, your current would be flowing, and in fault conditions this PNP would turn on and the red LED and the buzzer will sound, and you can get to know that the circuit is tripped and you need to reset it. And that's the reset switch, as I said. So all in all, yeah, that is the total circuit. And I think I've showed this is the data sheet of the P channel MOSFET. Can handle up to 55 volts between its drain and source, and we have only 12 volts, and it can handle quite a bit of current, so that's good too. And only 20 milliohm on state resistance, which is very low. So now that the circuit overall, now that you know how it works, it's going to sense the voltage across the current shunt, compare it to your set voltage, accordingly set or reset the SR latch, and keep the current flowing or stop it. And we have the reset switch. So now that the circuit is explained on the schematic, we'll go to the breadboard. So here we have the breadboard circuit, and this, as I said, the 22 ohm load, that's the load. And I've just put it was a little tough to put it inside the breadboard, but I could have used crocodile cable, but yeah, it fits, so it's okay. and there is the 1 ohm. You can't see it written, but this is the 1 ohm, which is going to be a current sensor resistor, and this is the actual load, which is 22 ohms. And everything is being powered from the 12 volt supply. It's set to 12 volts, and the comparator also has been given 12 volts, but the gate, you saw it, right? The 74HC only to between 2 and 6 volts, so we can't give that 12 volts. So just a 7805 regulator there, and there's the p channel MOSFET over there, and the NPN BJT, I don't think you can see it, it's below the 1 ohm. There it is, that's the NPN BJT, and there's the PNP BJT over here, and this is the 74HC00. I've used all the 4 gates and just some small jumpers there for the shorted inputs, and we have the pull downs there. Those are the 10k pull downs, and that's the reset switch, the tactile switch. And as I said, this is the comparator over here, and 150k and 15k, that sets 1.1 volts, so around 1.1 amp is our safe current. And finally, here are the audio visual indicators. If the green LED glows, that means your circuit is operating normally, and the red and the buzzer here, which would indicate the overcurrent. So if we divide the current load, which is 12 volts and 22 ohms, roughly around 500 milliamps is going to flow, and that's below the 1 amp current limit, so it should work normally. And to demonstrate the overcurrent, I have another 2 resistors here, and first I have a 33 ohm over here, and the second is a 10 ohm. So basically how to demonstrate it, I've pulled out these 2 wires which are just across this load resistor, and if we put this resistor in parallel with this, of course the resistance would decrease. So if you put 22 ohm in parallel with 33 ohm, it would roughly be 13 ohms or so, and the final current flowing would be around 800 or 900 milliamps, and that is still below our 1 amp limit. And so when I put this in parallel with this, the current should continue to flow, the overcurrent should not trigger. But if I connect this 10 ohm over here, the resistance will become 7 ohm or something, and the current becomes around 1.7 amps, which is going to be above our set limit. So with this we'll be able to demonstrate that the overcurrent triggers, and I'm going to show you both to make sure that this what triggers it and what doesn't. So first I'll just power up the circuit, and here I've switched it on, and you can see the green LED is on. So, and I'm also showing you the drop across the load resistor, and that currently says, not load, sorry, the current sense, and it says 0.466 volt. So basically that means, as I said, it's a 1 ohm resistor, so it means that around 460 milliamperes is flowing, and that's below our safe limit. So now I'm going to put this 33 ohm in parallel with it. So I'll just hold it here, and if I do that, just a minute, so I have the 33 ohm here. So if I touch this over here, you can see this is touching, and the current has gone to around 840 milliamps, but that is still within the safe limit. So you can see it is still green, it hasn't triggered yet. And now I'll switch to the 10 ohm load, and you'll see how it triggers. Now I'm holding the 10 ohm in my hand, and now I'll just touch it with this, and you can see that the overcurrent has triggered, and the voltage across the shunt has dropped to 0 volts. So basically the current has been cut off, and you can see the red LED and the buzzer are sounding. So to reset it, we have the reset switch, and that has turned off, and now it's back to the normal operation, and the 460 milliamps has begun to flow again. Now that you saw the overcurrent being demonstrated, we can show you 2 more things, and that shows how cool this is. One thing is, earlier I removed the load, right? The fault load after, and I pressed the reset switch. But let's say you don't remove the fault load and you keep it connected, and how is that going to work out? So we're going to see that. So let me just make sure that this is still touching it, and you can see here now it is the overcurrent has triggered, but the load is still connected. And what I'm going to do is I'm going to press the reset switch, but you're going to see that it's not going to allow the current to flow unless the fault input has been removed. So now I'm going to remove it and press it, and you can see same as before, the output has begun to turned on and the normal current is flowing. So unless you remove the fault input, the current is not at all going to be allowed to flow. And that shows that the overcurrent works. And let's say there's literally a short circuit over here. The current was still not a short, it was definitely above the rated current, but it wasn't a short. So we have these two wires, right, which are in parallel with the normal load. So if you short these, this is going to be practically 0 ohms. So to simulate a short, I will just touch these two together, and you can see that it would still be triggered. So here I'm going to touch this, and you can see that the output has cut off again. So yeah, it can protect against both overcurrent and short circuit. So it's a very versatile circuit and fully discrete. There are no digital components involved here, so the BOM cost is going to be much lesser than, you know, implementing maybe a Hall effect or something of those sorts. And if it's just a simple power supply or something like that, this circuit would work perfectly. And yeah, that was the whole demonstration. So yeah, I hope you know understood something about this, and maybe even implement it. That will be good too. Overcurrent is a very serious problem in DC circuits, and we do need to account for that. So yeah, thank you.